Pittsburgh, 1953. Inside a steel mill, a ladle holding 175 tons of molten metal moved slowly overhead. The workers below barely looked up. They had walked under that same crane hundreds of times. The steel glowed white at 2,900 degrees Fahrenheit. The ladle hung from a single hook, and the system was storing a failure it could not contain. Before we continue, if these industrial history stories resonate with you, I would be grateful if you could subscribe and let me know in the comments below which industrial disasters I should investigate next. Now, back to the story. This is not a story about explosions or boilers. This is about overhead cranes that carried liquid fire across factory floors, suspended above men who had no escape route and no warning system. By the 1950s, steel mills had grown to depend entirely on these machines. A single ladle could hold more molten metal than most furnaces produced in a week during the previous century. That concentration made production efficient. It also made containment impossible when things went wrong. Here is the question that defines everything that follows. Why did engineers accept molten steel traveling overhead in buildings where hundreds of workers stood directly beneath it? By the end of this story, you will understand the system, not just the accident. You will see why stopping was considered more dangerous than continuing, and you will learn why the trade-off between efficiency and exposure was never actually resolved. It was simply accepted. Steel production demanded heat, and heat demanded motion. In the early 20th century, steel mills operated on a principle of continuous flow. That molten iron left blast furnace and traveled to the Bessemer converter or open hearth furnace. From there, it moved to molds or ingot stations. Every step required transferring liquid metal at temperatures high enough to melt through brick, concrete, and human bone in seconds. The ladle became the solution to that problem. A ladle is a massive container, usually lined with refractory brick and mounted on a trunnion so it can be tilted to pour. Early ladles held 10 to 20 tons. By the 1940s, production demands pushed capacity far higher. Ladles weighing 50, 100, and eventually more than 150 tons became standard in large mills. These were not small buckets. They were industrial vessels the size of railroad cars, filled with glowing liquid that could burn through steel plate in moments. Mills built overhead cranes to carry these ladles because ground-level transport was slower and more dangerous. A crane allowed the ladle to travel directly from furnace to mold without obstructing the floor. It increased throughput and reduced the number of workers exposed to close contact with molten metal. That logic made sense on paper, but it introduced a new variable, height. When a ladle travels at ground level, a failure means molten metal spreads outward. Workers can see it coming and move. When a ladle travels overhead, a failure means molten metal falls. There is no time to see it, no time to react, and no safe direction to run. The danger moves faster than human reflexes. That difference mattered, but it was not part of the design conversation. Mills also favored cranes because stopping was expensive. A ladle full of molten steel could not be set down and reheated. Once the metal cooled below a certain temperature, it solidified. That meant lost material, lost time, and potentially a ladle that had to be broken apart to remove the hardened mass inside. Continuous motion kept production flowing. It also kept workers underneath. This is where the trade-off becomes visible. Cranes increased efficiency and reduced some risks. But they concentrated danger in a new way. Instead of spreading exposure across many small transfers, the system created single points of catastrophic failure. A dropped ladle did not spill metal. It released it from a height, turning gravity into an accelerant. Engineers understood the physics. They did not design for the failure. By the 1940s, the overhead ladle cranes had become standard across the United States steel industry. Mills in Pennsylvania, Ohio, Indiana, and Illinois all used near identical systems. The cranes were massive structures, often spanning the entire width of a building. They ran on rails mounted high on the walls, allowing them to move laterally while a trolley moved the hook back and forth. The ladle hung from a single hook attached to a steel cable. Here is what the reports did not measure. That single hook represented the only thing standing between 175 tons of molten steel and the men below. If the hook failed, the cable snapped, or the trunnion gave way, there was no backup. The ladle fell. Modern engineering calls this a single-point failure. At the time, it was called standard practice. Ladles grew heavier as mills expanded. In 1900, but a large mill might process 500 tons of steel per day. By 1950, daily output exceeded 5,000 tons in major plants. That tenfold increase required moving more metal faster. Ladle capacity followed production. Some mills operated ladles exceeding 200 tons when filled. The crane systems were upgraded to match, but the fundamental design stayed the same. One hook, one cable, no redundancy. Speed mattered as much as size. Molten steel begins to cool the moment it leaves the furnace. If the metal temperature drops too far before pouring, it cannot flow properly into molds. This created constant pressure to move ladles quickly. Crane operators worked under time constraints that left little room for caution. Delays meant ruined batches. Ruined batches meant lost revenue. That pressure filtered down to every decision made on the floor. As workers developed routines around these cranes, they learned to judge crane position by sound and shadow. They timed their movements to avoid being directly underneath when a ladle passed. But mills were crowded spaces. Furnaces, molds, rolling equipment, and material storage all competed for floor area. There was no part of the building that was not occasionally beneath a crane path. Avoidance was a skill. It was not a solution. The danger was invisible because it was constant. Men worked entire shifts under cranes carrying molten loads. The system became familiar. Familiarity replaced caution. This is where normalization of risk takes hold. When a hazard is present every day without incident, the mind stops registering it as a threat. The absence of failure becomes evidence of safety. It is not. This is not just about cranes. It is about a production system that could not tolerate interruption. Steel mills operated on tight schedules, driven by customer demand, labor contracts, and fuel costs. Stopping a crane meant stopping a furnace. Stopping a furnace meant idling an entire production line. The cost of caution exceeded the perceived cost of risk. That calculation was made hundreds of times per day in every mill without formal acknowledgement. But as we are about to see, the system was not actually managing risk. It was deferring it, and deferred risk does not disappear. It accumulates. Crane cables were made of braided steel wire, designed to handle enormous tensile loads. A typical crane cable in a large mill could support over 300 tons under ideal conditions. But conditions inside a steel mill were never ideal. Heat, vibration, chemical exposure, and repetitive stress all degraded cable integrity over time. Engineers knew this. Maintenance schedules were written to account for it, but maintenance schedules were also negotiable. Here is what made cable failure especially dangerous. Steel cables do not break evenly. Individual strands fray and snap over time, reducing overall strength without obvious external signs. A cable could lose 30% of its load capacity before showing visible damage. Inspections were conducted, but they relied on visual assessment and manual testing. X-ray inspection did not exist. There was no way to see inside the cable to measure hidden wear. The hook itself was a massive forged steel component designed to resist shear and bending forces. But hooks were subject to a different kind of stress. Every time a ladle was lifted, the hook bore the full dynamic load. That load was not static. It shifted as the crane accelerated, decelerated, and moved laterally. These dynamic forces introduced stress cycles that fatigued the metal over time. Fatigue is not obvious. A component can appear solid and intact, while microscopic cracks grow deep inside the material. Each lift, each shift in weight, each temperature fluctuation adds another cycle. Eventually, the accumulated damage reaches a critical threshold. The hook does not bend, it fractures. And when it fractures under load, there is no gradual failure. The break is instantaneous. Ladle trunnions presented a third failure point. A trunnion is a pivot mechanism that allows the ladle to tilt for pouring. It consists of steel pins mounted on opposite sides of the ladle body, resting in brackets attached to the crane hook. The entire weight of the ladle transfers through these pins. If a pin shears or a bracket cracks, the ladle loses stability. In some cases, it can tip. In others, it can detach entirely. What do you think? Could a system this complex be safely managed with the technology available in the 1950s? Let me know in the comments below. Trunnions were exposed to intense heat every time molten metal entered the ladle. That heat caused expansion. Cooling caused contraction. This cycle repeated dozens of times per day. Over months and years, the expansion and contraction introduced stress fractures that inspections often missed. The fractures grew in locations hidden by the ladle body or obscured by slag buildup. Mills conducted inspections, but the frequency varied. Some plants inspected crane components weekly. Others stretched intervals to monthly or longer when production demands increased. Inspection records were kept, but enforcement was inconsistent. A worn cable or cracked bracket might be flagged for replacement, then deferred if the component still appeared functional. This is where operational pressure overrode engineering judgment. The men operating the cranes were skilled, but they were not engineers. They relied on feel, sound, and experience to judge when something was wrong. A slight vibration, an unusual noise, or a hesitation in movement might signal a problem, but these signs were subtle. In a mill filled with constant noise, heat, and motion, detecting early warnings required perfect conditions and focused attention. Neither was guaranteed. What made this system especially fragile was its dependence on sequential reliability. The cable had to hold. The hook had to hold. The trunnion had to hold. If any single component failed, the entire load was lost. There was no backup mechanism to catch a falling ladle. There was no secondary support. The design assumed that each part would perform as intended every time, without exception. That assumption was tested daily. Failure was not theoretical. Engineering journals and insurance records from the period document multiple ladle drop incidents. In some cases, the cable snapped due to hidden fatigue. In others, the hook fractured under dynamic load. Trunnion failures were less common but more catastrophic, as they often caused the ladle to tilt and spill before falling. Each incident followed a similar pattern. No warning, no time to react, immediate release of molten metal. But this is where the story turns, because the danger was not limited to mechanical failure. Human factors played an equally critical role, and as we are about to find out, the most dangerous failures were the ones that looked routine. Crane operators worked from enclosed cabs mounted on the crane structure itself. The cab traveled with the crane, giving the operator a view of the floor below. But that view was limited. At night or during heavy smoke, visibility dropped to almost nothing. Operators relied on spotters, hand signals, and radio communication to navigate. Any breakdown in communication could result in a ladle being positioned incorrectly or moved while workers were underneath. Training for crane operators varied by mill. Some facilities required months of supervised practice before allowing an operator to handle live loads. Others provided minimal instruction and relied on on-the-job learning. There was no national standard, no certification process, no uniform curriculum. A man could operate a crane carrying 175 tons of molten steel with less formal training than required to drive a commercial truck. Fatigue compounded the risk. Crane operators worked the same 12-hour shifts as other mill workers. By the end of a shift, reaction time slowed. Judgment deteriorated. Small mistakes became more likely. A slight misjudgment in speed or positioning could cause a ladle to swing. If the swing was severe enough, it could destabilize the load or overstress the cable. These were not dramatic errors. They were subtle lapses that added stress to an already strained system. Mills operated continuously, day shifts, night shifts, weekends, holidays. The cranes never stopped moving. This meant maintenance had to be performed while adjacent cranes remained operational. Workers would repair one crane while another moved overhead, carrying a live load. The risk of working beneath an active crane was understood. It was also unavoidable. Production could not stop. Communication failures were common but rarely documented. A spotter might signal too late. A radio might fail due to interference or dead batteries. An operator might misinterpret a hand signal in low light. These breakdowns did not always result in accidents, but they created near misses that went unreported because nothing had actually failed, or the system survived on luck as much as design. Here is the part that rarely makes it into textbooks. The men on the floor understood the danger better than the engineers who designed the system. They developed informal safety practices that were never written into official procedures. They learned which crane operators were reliable and which were careless. They memorized the sound of a healthy cable versus one that was fraying. They timed their movements to avoid crane paths during pours. This knowledge was passed worker to worker, not manager to worker. But informal knowledge is fragile. When experienced workers left, the knowledge left with them. New workers had to learn the same lessons, often through near misses or accidents. There was no institutional memory, no documented best practices. Safety depended on individual awareness, not system design. That is not safety. That is chance. The mills knew this. Insurance companies knew this. Trade journals published articles warning about overhead ladle hazards as early as the 1920s. But the recommendations focused on inspection and training, not redesign. The assumption was that the system itself was sound. Failures were attributed to human error or deferred maintenance, not structural flaws. This framing allowed the system to persist unchanged. By the early 1950s, the United States was producing more than 100 million tons of steel per year. Hundreds of mills operated ladle cranes daily. Thousands of workers passed underneath them. The scale of exposure was enormous. Even a small failure rate translated into significant casualties. And the failure rate was not small. What happens when a system depends entirely on nothing going wrong? We are about to find out. When a ladle drops, the event is over in less than 2 seconds. There is no time to shout a warning, no time to run. The ladle falls from a height of 20 to 40 feet, depending on crane position. Gravity accelerates it instantly. By the time it reaches the floor, it is traveling at more than 30 miles per hour. The impact is catastrophic. The ladle does not land intact. The refractory lining shatters on impact. The steel shell ruptures. Molten metal erupts outward in all directions. The initial splash travels faster than man can move. Workers within 30 feet are caught in the first wave. Those farther away have seconds to react. But seconds are not enough when the floor is crowded with equipment, materials, and other workers. Molten steel at 2,900 degrees Fahrenheit does not burn in the way fire burns. It destroys. It melts through concrete floors. It ignites anything combustible instantly. It vaporizes water into explosive steam. Workers caught in the initial wave are killed instantly. Those farther away suffer burns severe enough to be fatal within hours. Survivors often lose limbs or eyesight. The medical term is thermal trauma. The reality is far worse. The secondary effects multiply the damage. Smoke and steam fill the building within seconds. Visibility drops to zero. Workers attempting to flee cannot see. They collide with equipment. They trip over debris. Some fall into the spreading metal. Others are trampled in the chaos. Emergency lighting fails because electrical systems are damaged. The mill goes dark. Fire suppression systems are designed for fuel fires, not molten metal. Water makes it worse. When water contacts molten steel, it flashes to steam instantly, creating explosive pressure that throws metal farther. Sand and dry chemical suppressants are more effective, but they are rarely positioned close enough to the impact site to be useful in the first seconds. By the time responders reach the area, the damage is done. Evacuation is nearly impossible. Steel mills are designed for production, not escape. Walkways are narrow. Exits are few. Equipment blocks direct paths. Workers farther from the initial impact hear the crash but cannot see what happened. They do not know which direction is safe. Some run toward the sound, trying to help. Others freeze, unsure where to go. The mill was never designed for rapid evacuation under crisis. In documented ladle drop incidents, casualty counts ranged from single digits to more than a dozen, depending on shift size and proximity. But the numbers do not capture the full scope. Survivors carried injuries that ended careers. Families lost primary earners. Communities lost experienced workers. Mills lost production for weeks during repairs. The cost was measured in lives, livelihoods, and economic output. Investigations followed every major incident. Teams examined the failed components, interviewed survivors, and reviewed maintenance records. The findings were remarkably consistent. Cable fatigue, hook fracture, trunnion failure, human error, deferred maintenance. Each report identified a cause. Few identified the system itself as the problem. Why did the same failure modes keep occurring across different mills? Because the design was identical, the pressures were identical, the trade-offs were identical. Each mill operated under the same constraints: continuous production, minimal downtime, maximum throughput. Those priorities shaped decisions at every level. Safety improvements were adopted only when they did not interfere with output. That boundary defined what was possible. But here's what changed after the worst incidents. Not the design, not the system, the response. Insurance underwriters began requiring more frequent inspections as a condition of coverage. Mills that experienced drops saw premiums increase significantly. That financial pressure drove some improvements. Cables were replaced more often. Hooks were tested more rigorously. Trunnions were inspected after every major pour. These changes reduced the frequency of failures. They did not eliminate the risk. Some mills installed secondary support systems, a backup cable or a catch platform beneath the crane path. These systems were expensive and complicated to retrofit into existing buildings. Adoption was slow and uneven. Large, well-funded mills made changes first. Smaller operations delayed. The improvements helped, but they were not universal. Regulatory pressure also increased. State labor departments and federal agencies began documenting ladle incidents more systematically. Industry standards were revised to include more stringent maintenance requirements. But standards are only effective if enforced. Enforcement was inconsistent. Some mills complied fully. Others did the minimum necessary to pass inspections. Worker advocacy played a role as well. Unions began demanding safer conditions in contract negotiations. In some cases, workers refused to operate under cranes that had not been recently inspected. These actions forced management to take maintenance seriously. But the leverage was limited. In a competitive industry, mills that spent heavily on safety risked being undercut by those that did not. The real shift came from technology, not regulation. By the 1960s, electric arc furnaces began replacing some open hearth and Bessemer operations. These furnaces were smaller, more flexible, and required less molten metal transfer. The need for massive overhead ladles decreased. Some mills transitioned to ground-level transfer systems using insulated channels and automated controls. These systems eliminated the height variable entirely. But the transition was gradual. Many mills continued using overhead cranes into the 1980s and beyond. Some still operate today, though with significantly improved safety systems. Modern cranes include redundant cables, automated load monitoring, and emergency braking systems. The hook is no longer a single point of failure, but a fundamental principle remains. Molten metal still travels overhead. Workers still walk beneath it. The risk is managed, not eliminated. Here is the lesson written in steel and flesh. Efficiency and safety are not opposites, but they are not naturally aligned. Every system that prioritizes throughput will eventually test the limits of safety. When those limits are exceeded, the cost is immediate and irreversible. The ladle did not fall because engineers were ignorant. It fell because the system could not afford the alternative. The 175-ton beast taught industry a principle that still defines heavy manufacturing. If energy is stored, it must be controlled. If a failure is catastrophic, the design must assume it will occur. Redundancy is not a luxury, it is a requirement. And the workers who stand beneath the machine deserve a system that protects them, not one that depends on luck. This video is for educational and historical commentary purposes only. Please do not attempt to recreate hazardous industrial conditions. Thanks for watching. I hope this story gave you a deeper understanding of the systems that built modern industry and the costs that came with them. If you want to see more stories like this, let me know in the comments which industrial disaster I should investigate next.